Your gaming GPU has thousands of cores, but an AI chip has millions, and they're not even the same kind. Here's why. By the end of this video, you'll be able to explain to anyone why a gaming GPU and an AI chip are cousins but not twins, and why that difference changed everything. If you watched our last video on CPUs versus GPUs, you know that GPUs are incredible at doing the same task over and over again, really fast. Gaming GPUs draw millions of pixels. AI training repeats the same math billions of times. GPUs work for both. But here's the thing. They weren't built specifically for AI. They were built for graphics. And it turns out, AI does one very specific type of math over and over and over. That's matrix multiplication. And when NVIDIA realized that's all modern AI does, they said, what if we didn't build a general-purpose GPU anymore? What if we built something specialized? Something designed from the ground up to multiply matrices? That's what happened, and that's why an AI chip isn't just a GPU with more cores. It's a fundamentally different animal. Let me explain what matrix multiplication actually is, because this is the cornerstone of everything. An AI model has billions of numbers inside it called weights. When you train the model, you take those weights and multiply them by your training data. That sounds simple, but it's not. Imagine you have a checkerboard. One checkerboard represents your weights, another checkerboard represents your data. To multiply them together, you go across a row in the first checkerboard and down a column in the second checkerboard. For every pair, you multiply the numbers together, then add all those results. Then you do that for every possible row column pair. Just that, over and over, billions of times. Here's a simpler way to think about it. Imagine you have two shopping lists. List A has 5 items with prices. List B has 5 items with quantities. To find the total cost, you multiply each price by each quantity, then add everything up. That's matrix multiplication. Now imagine instead of 5 items, you have 10,000 items. And instead of doing it once, you do it a billion times per second. That's AI training. A gaming GPU can do this. It has thousands of tiny cores, and they can all multiply numbers at the same time. So you can multiply lots of pairs at once, but here's the problem. Those cores are generic. They can do any math. They're like workers who can do any job. Matrix multiplication is just one of many things they could do. So NVIDIA asked a better question. What if we built cores that could only multiply matrices? What if that was their entire job? What if we specialized them completely? That's a tensor core. A tensor core is a tiny machine built to do one job. Multiply 2 matrices together. That's literally all it can do. It can't draw pixels. It can't handle random math. It just multiplies matrices. And because that's all it does, it can do it incredibly fast. It's like having a worker who's trained their entire life to do one thing. They're not as flexible as a generalist, but they're 10 times faster at their specialty. Here's the difference. A gaming GPU core can do many different operations. A tensor core can do one operation, but it does it optimally. The architecture is built around matrix math. The memory is organized for matrix math. The instructions are designed for matrix math. Everything about it is specialized. Think about it this way. Imagine a factory that can make anything, chairs, tables, cars, whatever. It's flexible. It can switch from making chairs to making tables to making cars. But it's slow at each one because it has to reconfigure for every product. Now imagine a factory that only makes pasta. It can't make chairs. It can't make cars. But it makes pasta so fast and so efficiently that nothing else matters. That's the difference between a gaming GPU core and a tensor core. NVIDIA's A100 chip has 5,120 tensor cores. The H100 has 14,080 tensor cores. These aren't generic cores. Each one is a specialized pasta machine for matrix math. Here's why this matters. When you train an AI model with a gaming GPU, the GPU has to handle matrix multiplication, but it's also doing a lot of other overhead work. Memory management, instruction scheduling, data routing. The generic cores can handle it, but it's like asking a generalist doctor to do surgery. They can do it, but it takes time. When you train on a tensor core processor, the entire chip is built to move data to the matrix multipliers, do the multiplication, and move the result back. No wasted motion, no generic overhead, just pure multiplication. Let me give you the real-world numbers. Training GPT-3 on a gaming GPU would take weeks. Training GPT-3 on an H100 with tensor cores takes days. Not because the H100 is twice as fast, but because every single part of the architecture is designed to multiply matrices efficiently. Think about what this means for the forward pass and backward pass in neural networks. In the forward pass, you multiply your input data by all the weights in your model. In the backward pass, you adjust those weights based on whether the model was right or wrong. That adjustment involves more matrix multiplication. Forward pass, multiply. Backward pass, multiply. That's training. A gaming GPU does this. An H100 does this, but with every transistor optimized for matrices. This is why every AI company is fighting over the same chips. OpenAI uses H100s. Google uses TPUs, which are their own specialized tensor processors. Meta uses NVIDIA Tensor core chips. Microsoft uses both. Everyone needs the same thing, hardware built specifically to multiply matrices. NVIDIA didn't just add more cores to their GPU. They redesigned the entire architecture. The memory bandwidth is optimized for matrix sizes. The instruction cache is optimized for repetitive matrix operations. The power delivery is optimized to keep tensor cores running fast. It's not a bigger GPU, it's a different tool for a different problem. Here's the historical evolution. Gaming GPUs have been around since the early 2000s. They were built to draw pixels. Then, in the 2010s, people realized GPUs were perfect for AI training. For a while, gaming GPUs worked fine. But as models got bigger and bigger, people realized, we're not using the GPU to do anything except matrix multiplication. We're throwing away all the flexibility of a gaming GPU and just using it as a matrix machine. So NVIDIA said, why make a flexible tool when we can make a specialized tool? Why give people all these generic cores when they only need matrix cores? That decision changed the AI industry. A gaming GPU is still a GPU. It can draw pixels, do random math, handle graphics. But an AI chip is not really a GPU anymore, it's a specialized tensor processor. The word GPU is still there for historical reasons, but architecturally they're cousins, not twins. Here's something crucial. A gaming GPU from 2015 cannot run modern large language models efficiently. An AI chip from 2015 could. Why? Because the gaming GPU was never designed for the scale of matrix multiplication that modern AI requires. The AI chip was. Specialization solved a problem that generalization couldn't. Now here's something important. If you've been following along, you understand the core mechanism. Tensor cores are specialized hardware for matrix multiplication. That specialization is why AI training is possible at the scale it's at today. And if you want to understand more mechanisms like this, I'd really appreciate it if you hit subscribe. Every new subscriber helps us make more of these videos. Also, if this clicked for you, smash that like button. The YouTube algorithm rewards it. And comment below, what mechanism do you want us to crack next? What have you always wondered about? How does encryption work? What is load balancing? How do banks create money? How does blockchain actually work? Drop it in the comments. The more votes a comment gets, the sooner we make that video. That's literally how we decide what to explain next. So help us decide. Let's crack the next one. So what does this mean in practice? If you're building anything with AI, you're not training on a gaming GPU if you care about speed. Your RTX 4090 can fine-tune small models on small datasets. But if you're training a language model, you're renting H100 time in the cloud. That's why every AI startup is paying thousands of dollars per month to AWS, Google Cloud, and Azure. Not because your gaming GPU isn't smart, but because serious AI training requires specialized hardware that multiplies matrices at scale. The bottleneck in AI isn't smarts anymore, it's compute. It's access to the right chips. And right now, NVIDIA controls that supply because NVIDIA built the only chips that are specialized enough to do what modern AI needs. This also means that as AI models get bigger, the demand for specialized tensor processors only grows. TPU v5, H100s, whatever's next. The future of AI is not bigger GPUs. It's more specialized hardware. Hardware built for the specific work that needs doing. Here's the bottom line. A gaming GPU is a generalist. It can do many things, including matrix multiplication. A tensor core is a specialist. It can only multiply matrices, but it does it so well that it's the only reasonable way to train modern AI. Gaming made GPUs affordable and accessible. But AI specialization demands meant the hardware had to evolve. And now, the chips that power ChatGPT, Claude, and every major AI model are not graphics cards anymore. They're specialized tensor processors, cousins to the gaming GPU, but fundamentally different in their design and purpose. If you've made it this far, you understand the mechanism. You can now explain to anyone why a gaming GPU and an AI chip are cousins but not twins. You know what matrix multiplication is. You know why tensor cores exist. You know why every AI company is competing for the same specialized chips. And you understand that the bottleneck in AI isn't smarts or innovation, it's hardware. If you want to crack another mechanism, hit subscribe. Like this video if it clicked for you. And comment what mechanism you want next. See you in the next episode.